First of all, welcome to our first LinkedIn live stream. I'll just start in a couple of minutes. I'll say a few words because we need everybody to attend. We're going to cover RF DACs and RF ADCs this morning in the context of how they're used in our Proteus arbitrary waveform transceiver. And we're going to talk about electronic warfare and radar. Under the context that this is a global LinkedIn live stream, so we're not going to go into too much details of electronic warfare, apart from waveform generation and some of the obvious test requirements that are publicly available and freely available on the internet. So let's first start. So I've got a bunch of examples. I got some spectrum analyzers running here. I've got on this side, I've got the spectrum analyzer. On this side, I have the instrument that we use in a P9484M. And so we're going to connect from the computer that's here right in front of me to those to do some measurements. And I've also got a slide deck. So if I minimize myself a little bit now and go over to here and get this up. So welcome. This is how to use RF DACs and ADCs for EW. I'm Mark Elo, your host for this live stream this morning. Any questions, please make a comment. I'm not sure if we'll get round to answering them, and of course, also due to the sensitivity of the subject, I prefer to answer them offline as well, personally with you. We're going to talk about the Proteus arbitrary waveform transceiver this morning and how we utilize some RF DAC and RF ADC technology and a programmable FPGA as well. So let's go on to the next slide. So let's talk about Tabor, our history. Tabor has been in business since 1971. We've been making arbitrary waveform generators since then. Our customers are usually scientists and engineers. We've been a major OEM supplier over many, many years. More recently now, we've decided to relaunch our own brand and sell Tabor products. And on the back of that, we've developed a lot of new technology, especially with respect to RF generation, multi-channel RF generation in small form factors, combined with a set of amplifiers for physicists, for RF engineers, for communications engineers, etc. We've moved up our sample rates to quite high sample rates, and we work on the performance end of signal generation and signal simulation. So this is what we're going to go through this morning. First of all, I'm going to define the problem, and to do that, we'll use a simplified generic airborne EW system as an example. We'll talk about the test requirements for that. Then I'm going to introduce you to direct digital conversion, the core of this presentation this morning. Then we'll show you how to essentially build one. And one of the tenets of this is that we built one, right? And so you, as an in the engineering community, you're always making build versus buy. And, obviously, as an equipment manufacturer, I'm going to make the case for, first of all, why direct digital conversion is good. And the second is why you shouldn't build your own and you should buy a ready-made system like ours. So we'll create a direct digital system, and I'll show you the block diagram of that. And that's all based around the Tabor Proteus arbitrary waveform transceiver. So we took the concept of an arbitrary waveform generator and added a digitizer with a fast FPGA in the middle. So that's how we get to a transceiver. And then we'll look at the data and signal flow. Very important for any kind of electronic warfare or radar application is how you perform waveform scheduling. There's a number of ways. I'll cover one because we only have an hour. I've got some Python examples. We'll cover multiple Nyquist zones, coherent pulse modulation. We'll look at bandwidth of the system and some of the considerations. And of course, we want to do more than pulses, so we'll examine one of the MATLAB tools that we have to do advanced signal creation. And both the Python examples and the MATLAB readily available on our GitHub site. I look at closed loop, obviously, because we've got an RF DAC and RF ADC, and with an FPGA in the middle, so we can do things in between. And so we don't have to rely on an external controller in some cases. And then we recap and summarize. So that's what I'd like to talk about today. So let's go through. Let's have a look at, first of all, defining the problem. So here's our generic EW system. So we have 4 antennas, one on the nose, one on the tail, one on each wing, and we have an EW system in the middle. And in this slide, we have a threat, which is a single emitter in this case. And, you know, it's transmitting, and it's the job of the aircraft to send a countermeasure back to fool the emitter. And we want to test this scenario both in the lab and out on the range as well. So if we look at a typical receiver with the Army Navy nomenclature at the top, AFR system, it's usually 4 antennas that connect to the radar warning receiver here, and then in the cockpit there's usually a display which tells you the direction the threat is coming from. So that's why we have 4 antennas, so we can do some angle of arrival measurements to determine the position of the threat, to be able to determine how we countermeasure the threat. And you know, you're going to use electronic test equipment to test this, to act like the emitter, you know, for both manufacturers as part of product verification. And once there's product acceptance, we test and evaluation, and of course there's range testing and equipment that I'm going to talk about today, and the utilization of RF DACs and ADCs are used all the way across this product life cycle here. So let's do a deeper dive into our radar warning receiver. In this particular generic receiver, we have 4 antennas that goes into the detecting system. Then there's a measurement system, again, to determine angle of arrival, and also to begin to drill down on what the pulses represent in terms of a threat. So what threat is this radar connected to? And then we have the identify the threat. So what's going to happen in our electronic order of battle, and is this one that we've identified? It goes up on the display. We know what the threat, we know what the radars, the emitter's connected to, so we take an action and we deploy a countermeasure. So essentially we need to create some kind of EW test system that connects to one of these 4 antennas in this simplified model that we're looking at today. And there's, in my mind, there's actually three classes of EW test system. So there's a simplest one, which is a static kind of scenario generator. So what we're doing is generating a stream of pulses, a stream of RF pulses that represents a specific threat. And if the radar warning receiver receives those pulses, it lights up and says, yeah, I've detected this missile connected to this radar. That's the simplest one, no movement. And then there's a middle case of dynamic real time. So now there's some movement in, so you can emulate the aircraft flying around doing a figure eight or a racetrack. This uses a few more channels because it's got it can generate a few more emitters, and it's usually solved with a fast tuning coherent RF signal generator, probably connected to a wideband arbitrary waveform generator. This one here is just probably a standard signal generator from one of the larger manufacturers of test equipment, and or a wideband arbitrary waveform generator. So this goes from a single unit to maybe a stacked unit of systems with some generic scenario generation software around it. And, you know, we've got low pulse per second, medium pulse per second, and then we get to the big one. So large scale multi-emitter systems, high amount of pulses per second. This has got real-time mission software that's running, so it can emulate, you know, flying down the Straits of Taiwan, or, you know, anywhere that you may have some threat information, and you can really test the instrument, test the radar warning receiver in a real life scenario. So this is what I would call a specialized digital generator and RF generation system. And you can find out more by looking at sites of, say, SRC or Northrop Grumman, who specialize in this kind of equipment. So, you know, we want to be able to play at least a simple scenario. And so what we want to do is if we look at this down here, we want to emulate something like this. So maybe we're an aircraft, right? And we're flying in, and we're generally low observable. We've got some kind of stealth technology going on, but we do get picked up by a long range radar, which then communicates to the control van, which then tells the short range radar to go look at it, see if you can get a target track and lock on. You know, when there's a lock, you know, there's a battery that's activated, the missile fires. It uses some missile track. The missile's controlled for the van. When it gets closer, it goes into its own command guidance, active home, gets close enough, has some fuses, and pop, there it goes. And it's the job of the radar warning receiver and the ECN system in the aircraft to try and stop this happening. So you could use things like anti-radiation missiles, standoff jammers, or the built-in ECM system within the aircraft, whether that's you know, chaff or something more advanced like digital RF memory. So what we have to do to help test this for this scenario is generate simultaneous multiple emitters. We have to be able to cover the relevant frequency bands, C band, X band, S band. We have to be able to emulate the bandwidth of the emitters. You know, some of these radars may have hop sequences that go over a large frequency range, maybe 1 gigahertz, 2 gigahertz. You know, once we get to the active home, this could be a high frequency, linearly frequency modulated signal, a chirp. So we have to be able to, within the bandwidth of our transmission, create these different types of emitters. We need frequency coherence. We have to act like a radar. So from one pulse to another pulse, we have to switch the carrier on and off, and not just generate random frequencies all starting at 0 phase every time we do a pulse. We have to be able to emulate for different rise, fall, peaks, droop, etc., because sometimes to ID a specific threat, we need more details than just what the pulse repetition interval is and the frequency of transmission. So these are accurate pulse emulation is very important. We need to be able to emulate modes. That should say mode emulation. So we need to do, you know, some longer range, shorter range, LFM, as the target gets closer. And then we also want to make sure that when we're doing these angle of arrival measurements, that pulse timing and alignment channel to channel is excellent and also programmable, because we, like I said earlier, we do definitely in this middle range of scenario generation want to be able to emulate movement. Okay, so that now I hope with you all we framed as the problem that we're trying to solve and how we would like to solve the problem. Do that with RF DAC technology and RF ADC technology. So let's give you an introduction for those of you who have not used a digital RF DAC before. But it's quite simply, in essence, a digital implementation of an IQ modulator. So we have an analog modulator here, and you can see we have I and Q, some filtering. We have our local oscillator. This sine wave here represents the LO, and we have a mixer, and then we have a quadrature mixer. So this one's 90 degrees out of phase with this one. This gives us our IQ modulation. We sum it here and then transmit. Different to an AM modulator, it doesn't create sidebands. We just create one carrier that is centered on the frequency of the local oscillator. And we essentially implement that digitally. So we put I and Q in. We've got some low-pass filter in here. We have the complex mixer. We have this thing here called a numerically controlled oscillator, which is essentially a lookup table of sine waves, if you're familiar with how you do that. And we can produce a sine and a cosine coming out of there. So it's a direct digital synthesis technology in NCO DDS. And I have another presentation that covers DDSs that you can ask me for as well. But there's plenty of information on the internet. So we create the sine, we create the cos, we go into the complex mixer, do a little bit of filtering, and output directly to RF. So this is the digital rendition, or the digital version of the basic analog modulator. So there's things I need to talk about as well: clock, bandwidth, and frequency range. So our clock, so if we look at a DAC here, we have a clock, and in our Proteus arbitrary waveform transceiver and the DACs that we're using, our maximum clock rate is 9 gigasamples per second. So what does that mean? So we have to look at what the Nyquist sampling criteria is. So the clock needs to be at least 2 times the sample rate of its high frequency component for the first Nyquist zone. So if we have the clock here and we generate a signal at 1 gigahertz, and this is clock divided by 2. So this is the first Nyquist zone. And if you just wanted to use the first Nyquist zone, you would filter around this between 0 hertz, say a few hundred kilohertz, up to 4.5 gigahertz. But you know, there's cost advantages to not doing that. And simplification in the block diagram as well. So we could actually use the second Nyquist zone or the third Nyquist zone. So here we have clock. So if we've generated a signal at 1 gigahertz, then we would see that signal at clock minus 1 gigahertz and clock plus 1 gigahertz. So this is at 8 gigahertz and this is at 10 gigahertz. And so now we've got all these different frequencies that we can utilize. The problem, or the fall down with it, is that, you know, the amplitude rolls off in a sine x over x fashion here. And so we lose amplitude, and each one of these now is closer to the noise floor of the DAC. And so the spur-free dynamic range increases. So I'm going to cover that and show you some of the performance of the DAC that we use with respect to using multiple Nyquist zones. So the chip that we're going to use today, and the chip that's at the heart of the transmission part of our transceiver, is the TI DAC 38 RF83. So on the chip, there's 2 DACs. We've got 4 IQ modulators, 4 NCOs. We can do bandwidths of 1 gigahertz, 2 gigahertz, and 4 gigahertz. It's a 14-bit resolution chip, but we zero-pad it to 16 bits. Maximum sample rate, already talked about, 9 gigasamples. We've got 2 of the interpolators turned on in our product, 4 and by 8. RF power at 2.1 gigs, about 0 dBm, and IMD3 70 dBc. So baseline specs. So as we go through this, we'll be able to understand what these specs mean to scenario generation. If we look at the chip here, this would be channel 1 of our instrumentation. This would be channel 2, the differential outputs. And within each output, we have 2 IQ modulators. So on each channel, you can generate up to 2 independent RF signals. So this is channel 1, this is channel 2. So you'll see that there's 2 of these chips inside one of our units. So we have 4 outputs. Each output's differential, so that you would see 8 connectors when we look at the block diagram. So let's get this chip and put it in a system. So we want to add FPGA memory and I/O. So this is a typical system here on the left-hand side. We need to add memory. That defines how many waveforms we can store and process. We need an I/O interface to get the data in and out. The data transfer speed depends how quickly you can react. The FPGA is your real-time deterministic manager. And then the DAC defines two things. It defines your vertical resolution, i.e. the quality of the amplitude of the signal. 16 bits is 64,000 different points. 8 bits is 256 points. And then the clock here defines the output frequencies you can achieve, and more importantly, the bandwidth, because the output frequency, of course, can be, you can use multiple Nyquist zones, as I talked about earlier. So let's put all that together in a more coherent block diagram. Got I/O, got FPGA, and we talk about the memory here in terms of segments. So we can define a segment length. We can put a waveform, call it segment 0, put another waveform in, call it segment 1, segment 2. And then you can also, when I get down to waveform scheduling, you can build series of these segments and play one maybe 100 times, one maybe 5 times, one maybe 2, etc. And this is just the transmission side. When I get to the receive side, you can see that we can influence what segment we play out based on what we receive. Got the DAC, and then you've got the output. And then optionally, you can add a balun, which if it's differential out, you can improve your amplitude a little bit, clean up the signal. You can use an amplifier, and also you can use a correction filter if you wish, to focus on a specific Nyquist zone of operation. So we use this DAC in the Tabor P9482/4M. So 2 means 2 channels, 4 means 4 channels. So if you go back to the block diagram of the DAC, one is using 1 DAC and the other one uses 2 DACs. So this would be, these are the differential outputs here: channel 1, channel 2, channel 3, channel 4. So if you're using, if you buy the version with 1 DAC, you get channel 1 and channel 2. If you buy the version with 2 DACs, you get channel 1, channel 2, channel 3, channel 4. And, if we go back to this takes into account, this is just a regular DAC, something like an arbitrary waveform generator. And here we've replaced the regular DAC with the RF DAC. So within this DAC, you can optionally switch it to be a high-speed direct digital to analog converter, or you can switch in the IQ modulator. And a third thing that you can do is actually just use the NCO on its own as a CW generator. So there's actually 3 modes of operation here in the DAC of the Proteus 9482M. That's a great segue onto this slide. So we have the waveform memory here. So this is what we play out of the memory that we looked at in our previous block diagram. I got it here now, called waveform memory. And then we have our complex mixer and NCO. So here's our NCO, and then here's our waveform memory. And you put those two, you make this into I and Q, and out comes a coherent pulse stream. We can have different rise fall times, overshoot, droop, anything we like on this signal, because we're defining it in arbitrary waveform memory. But you can see here that it's coherent. So if I keep, if you followed these here, when it switches back on, is as if the transmitter never switched off. So that's quite important when we want to emulate a radar signal. We also, added a digitizer. So we transmit, we can receive. There's a programmable FPGA, and we have 4 outputs and 2 inputs, essentially. So if we look at this in terms of a block diagram, like we looked at in our initial generic radar warning receiver, we have the opposite of that. So now we have 4 channels of transmit. Depending how many DAC chips you can use, it's 2 to 4 channels. We have a generation system. We have an analysis system, and we have a receiver system. And I'm going to talk about both, but there's two ways to do it. The speed here is reasonably fast, and the way we've done waveform management and data transfer is you can do some amount of offboard processing to be able to receive a signal, ID some pulses, and then say what's going to come out next. And then we also have an onboard processing system where this becomes a complete closed loop. Now, some of you may say, well, why don't you do this? We've got discrete DACs and discrete ADCs and an FPGA here. Why don't you just use a system on a chip? The fact is, it's about cost and COGS and performance. And you as a consumer, if you only need transmitters, you don't want to buy a full SoC system all the time. So we made the effort to split these into discrete components, because I may have 16 transmitters, I may have 24 transmitters, and they are transmitting based on a single signal received. Or the other scenario is I may have 2 receivers and 2 transmitters. I may have 4 receivers, 4 transmitters. I want to keep it modular, and we want to keep it in a way that's configurable at a cost point that's reasonable as well. So that's our block diagram. 16 gigasamples of memory. RF DACs are 5.4 gigasamples per second, and the RF ADCs are 5.4 gigasamples per second, and the RF DACs are 9 gigasamples per second, differential out, regular in on the digitizers. And then we also run PCI Gen 3 by 8 as well. So that's what gives us our fast transfer rate. So PCI is good because it sits on the bus of your computing device. There's no conversion to LAN, no conversion to not GPIB, but USB or RS-232. This is, as far as your control computer is concerned, this instrumentation sits on the PCI bus as if it was a sound card, as if it was a GPU, if it was a graphics card. I mean, a graphics card and a GPU are the same, but whether it's doing advanced math or supporting advanced graphics or creating signals, that's what this instrumentation does that. So a good design choice, I think, for us. It also has a fast memory as well. So, one of the things that, can you select a waveform with no a priori knowledge of what's coming in? And we've tried to achieve that within the system with a fast memory that allows you to select things within a few clock cycles of receiving the signal as well. So if you want to ask me more about that, please contact me. So let's put it all together. So what we've got here is our representative aircraft. It has an EW system. In the middle, the 4 antennas. We've got our single threat here. In reality, this would be surrounded by threads, and I'll get into that. And we have our detector, measure, identify, and then take action in the countermeasure system. So then here we have our Proteus system, this thing. Oops. And we've got 4 transmitters. We have the ability to generate signals. We have the ability to analyze, receive, and retransmit. So we can create a closed loop threat system there based on a single threat. So that's good. That's good. But I think we can go a little further. System requirements. One of the first thing is we want to be able to emulate simultaneous multiple emitters. And so this is just one, but in reality, your aircraft or whatever thing is being threatened would be surrounded by multiple radars. So I'm going to talk about that. We're going to then go on to frequency range. We're then going to talk about emitter bandwidth, frequency coherence, pulse modulation, mode emulation, and multiple channel pulse timing and alignment. and we're going to do a few demos. So we're now moving into the second part of the presentation, which is more demonstration and capabilities, and getting down to some real measurement results to be able to help you understand why we use the specific RF DACs and ADCs and how we put it all together. So first of all, I showed you one Proteus arbitrary waveform transceiver. It comes in two forms. It's the AWT, which is 3 slots wide, and it's the AWG, which is 2 slots wide. So if we want to generate 4 threads, 8 threads, 12 threads, 16 threads, you would use 8 channel units, 12 channel unit. I mean, you would put 4 of these together to get 16. But remember also that each output also has 2 IQ modulators. So technically you could be going up to 32 threads with just 4 of these grouped together. And you can connect as many of these together as you like. They would fit in the PXI, what we call the PXI chassis. This conforms to the PXI standard. We've just launched a new PXE 21100, which is a 21 slot chassis. So we utilize every single slot of this chassis for instrumentation. So we've moved the controller to the back plane, moved the center trigger out, and you get the industry's best channel per square unit volume of transmitters in this chassis. So you can have quite a lot of these in here. So let me do the math. So if it's 21, if they're 2 each, so that's 20. So it's 20 times 4, that's 40. Sorry, it's 10 times 4, so that's 40 transmitters in a 19-inch slot. Of course, you're not going to have only transmitters. You'll want some transceivers, and there are 3 slots per module as well. So it's 1 slot wider because this line of connectors here, that's the digitizer line. And these connectors here, by the way, are marker outputs. So these are TTL outputs that you can control things like power amplifiers for if you want to do transmissions on the range, for example, or switch any filters in and out, analog filters in and out. You would use these analog outputs here, real-time analog outputs. And they're coherent to the waveforms that you're generating. If you want more than 40 channels, we have a channel-to-channel sync module that allows you to sync. One channel would be a master. You can have multiple slaves, or you can have them all being exactly synced as well. So there's different configurations, different ways to create multi-channel synchronization. So that is how we address the simultaneous multiple emitters. We spent quite a few $1 million developing this technology. So if you were to use a DAC on your own, you'd have to figure out how you would create all these different emitters. So let's look at data and signal flow. There's an example. We keep all the examples as open as possible. So if you follow this link here, and the recording and the slides will be available afterwards. So we connect to the instrument, we define the pulses, we schedule the pulses, we add modulation, we transmit, we demodulate, we analyze, and then we make a decision. So this is, in essence, the data and signal flow of the Tabor arbitrary waveform transceiver. And when I want to spend a second or so talking about waveform scheduling with the FPGA that we've got. So we're trying to make a scheduler that is deterministic and within the FPGA, so it's all done in real time as opposed to trying to pass pulses over a bus all the time. So we created the waveform scheduler, and it consists of a number of tasks. So you can say task 1, play a pulse, task 2, play DC, task 3, play a pulse. And you can create sequences of tasks. So you could say task 1 is the pulse, is the PRI is long, so the target is far away. So you could have a far away set of tasks. And then as you get closer, the next sequence could be we've tightened up the pulse repetition interval. And then as you get even closer, You know, we've changed it now to an FMCW signal, so you could have sets of sequences that represent different modes of the radar. And the interesting part as well is that tasks can be changed based on real-time decisions from the digitizer. So I'll talk about that in the last few slides. But the digitizer can say, hey, I just received that. Instead of playing task 4, why not play task 5? And so we've got this whole real-time system built into the FPGA that allows us to create different sets of radar modes and react to what's going on in the outside world as well. And the way we've done it, you know, the things that we're trying to do is reduce the amount of waveform transfer across the PCI bus. PCI Gen 3 by 8 is super fast, but still we want to get it down to where you're only transferring a few sample points at a time and then letting the task tables, you know, generate the full pulses, generating the DC levels. And in order to reduce transfer time, because, you know, I've seen a lot of systems out there where you have to wait 5 minutes to load all the waveforms into the arbitrary waveform generator. Not 5 minutes, but, you know, a few minutes at least to load it into the waveform generator. And so that's a slow task. That's a slow thing to do. So that's why we developed the task table as a way for waveform scheduling. So what I've got behind me on my right-hand side, that's that side, is a Tabor Proteus. And we've already covered the block diagram. I've basically got the transmitter connected to the receiver with a short cable. And we're going to look at the RF DAC performance. We're going to do some receiving. We're going to look at how we do some real-time processing. And in most of them, we're transferring over the LAN here in the office. So it goes to PCI Gen 3, it goes to an embedded computer that we have in the instrument behind me. And we're going to transmit over LAN. Not super fast, but for this presentation, it's the easiest way. It's the easiest way to do the setup. So example 1, multiple Nyquist zones, amplitude, and SFDR. So let's have a look at that. So I'm going to minimize this now. This is where live streaming comes into its own, because we're actually going to get some code out. I said we'd look at some Python. Okay, so I think you can see this. So this is CW. So we're just going to generate CW so we can look at the multiple Nyquist zones. So we looked at in the block diagram of that slide. I generate a waveform here, and all I'm doing is making it the maximum DAC value of the arbitrary waveform generation. So I'm creating a waveform with DAC with I set to 1 and Q set to 1. I connect to the instrument over LAN. I select channel 1, set the sample rate, and here, this section here, I load that waveform into memory. Then I switch on the IQ modulator, source mode DUC, digital up converter. I use a by 8 interpolator. I use the IQM1 mode, which gives me a gigahertz of bandwidth. I reset the clock to the sample rate, to the interpolated rate, and I set the center frequency, in this case, to 1 gigahertz. Scroll on down. Here's the scheduling of the waveform. So I've only got one task in my task table, and that's going to be playing out segment 1. And then it says go to task 1 after completion. So I'm just looping around there. So if I go to here and run this, and it ran. So now I go to here. I've got a spectrum analyzer on the LAN. If I refresh, and it worked. Look at that, live streaming in full effect. So here's what we need to look at. So this is so the span of here is 13 gigahertz. So this is 1 gigahertz. So this is signal I generated. This here is clock over 2. This here is 9 gigahertz. So that is clock. So we've got a signal at 1 gigahertz, we've got a signal at 8 gigahertz, and we've got a signal at 10 gigahertz. So this is what I was talking about earlier, that we make all the different Nyquist zones available. So you can filter and choose which one you want to do based on your cost, signal density requirements. So now if I go back to the slides. So we just looked at this plot, but you know, we want to actually see what's in there, because we really want to understand what our spur-free dynamic range is and be completely transparent about it. So I knocked down the resolution bandwidth filter to a few kilohertz, 3 kilohertz, and you can see now that we've got a lot of different types of DAC spurs down here. Some of these are random, and some of them we have some algorithms to be able to cancel them out. It just depends on what type of DAC spur that we have. But you can see here at 10 gigs, that's where I've placed the marker. It's actually a nice clear space. So for X band, so if I tune in and zoom and set the span to 2 gigahertz, you can see we get a reasonable signal to noise ratio here of about 65 dBc. So that, you know, for a lot of application, in my experience, that's not bad, and something that is usable. So to recap, we connected, we defined a pulse, we set I to 1 and we set Q to 1, so that it's on all the time. We're just repeating it around and around, and we modulated it at 1 gigahertz, and it was simple as that. So just a few tens of lines of code to create that 1 gigahertz IQ modulated signal. Recapping the code, but it's pretty obvious. Connect, define waveform, schedule, modulate. So let's do this one now. Let's do this in let's do S-band, 2.2 gigahertz. And we'll also use the demodulator at the same time. So let me do this. Pulse mod dig, NCO. Let's run that. So we're running connected to the instrument, building the waveforms, no error, and here we go. So if I go back, so this I've just pulled across from the digitizer, and what we've got here is that I'm setting one waveform memory to 1 and another waveform memory to 0. So we play the first one time and then the second one 5 times. So we're keeping these pretty small and using the scheduler to create the different waveforms. So this is on once and this is off 5 times. This is I and this is Q. And then we can go over to our spectrum analyzer, refresh the page here. And now you can see we have modulation. This is the IQ modulation. Of course, if I could get closer to the spectrum analyzer, we could zoom in and we would see a spectrum that looks like this. So this is now showing the closed loop operation. And one of the key things to remember that this acquisition is coherent as well. So the phase and the amplitude, if I did this a million times, the phase and the amplitude would always come back the same, because what we're doing is, if I go back to the block diagram of the instrumentation, is that when we transmit here, we're telling the DAC to get ready to sample. So all the clocks are aligned, and so that gives you a coherent reception. So we demodulated and we analyzed in this case. Now, another one to look at is is frequency switching. So earlier I said, you know, if you use 2 channels, you get 2 gigahertz of bandwidth. If you use 4 channels, you get 1 gigahertz of bandwidth. So I created a little script here that jumps across the bandwidth of 1 gigahertz that jumps between the lower frequency and the upper frequency of the bandwidth. And we're centered here at 2.2 gigahertz. So let's have a look at that code. Let's have a look at that code. Yeah, here it is. So if I scroll up, it's very simple code. So I'm creating one set of sine waves that I is a cosine and Q is a sine, and then I create another set of waveforms that I is a sine and Q is a cosine. So this modulates on this gives us our high side, and this gives us our low side. So, and then we have the DC signal here. So if I look at the task table, our waveform scheduler, it's got 4 items. So we play waveform 1, high side. We play for 5 times the DC level. We keep that very small because we don't want to be transmitting a lot of DC across our backplane. It's going to hog your backplane and slow things down. And then we play the second segment, which is the low side signal. So that's segment 2. And then we play DC here for 5 times. So if I run that, I'll just close this window. If I run that, I have to find it first. Pulse. There it is. So I run that, and it's run. And so if we go to our spectrum analyzer, and here you can see. So the center frequency here is 2 gigahertz. This is 2 gigahertz here. So plus 500 megs that way, minus 500 megahertz that way. And again, at the second Nyquist zone. 2.2 gigahertz. So this is 9 gigahertz minus 2.2. So and then 9 gigahertz plus 2.2, and so on, all the way out to the higher Nyquist zones. And because we're going from one task to the other task, the frequency switching time is incredibly fast, and it's in the region of 100 picoseconds. 9 gigasamples. 1 divided by 9 gigasamples is 0.1 nanoseconds. So 0.111 nanoseconds. So that's how I got to 100 picoseconds. So we have great bandwidth and we have great frequency switching speed. I already talked about pulse-to-pulse coherence. We have the NCO on all the time. We have an IQ modulation, and we switch that on and off. I have a demo, but I think I'll skip that right now because it's pretty obvious and pretty straightforward. And we've been doing pulse modulation already, but we're already 45 minutes in, and we have to finish on the hour. Now we have all I did this time was just pulses, and I just used Python. We work equally well with Python and MATLAB, and we put together what we call our advanced radar demo. Let's see if I can run this live. Go to here. Press run. We've created a little GUI for it, and it allows you to do generate more advanced waveforms. Instead of you having to figure out how to do it, we provide the math for you. 192. A lot of companies have this kind of waveform generation software, but we've decided to make it open source and just a MATLAB plugin essentially. I think I'm on 16, 192.168.1.16, connect. There we go, we're connected to the instrumentation. We're going to do a coherent acquisition, so all our clocks are locked. That's what this means. We're using digital down converter, we're using the digital up converter. Remember I said we have actually 3 modes, but we're looking at 2 here. IQM1, which gives us a gigahertz of a bandwidth of 1 gigahertz, and IQ mode half, which gives us a 2 gigahertz, but you only get 2 channels of transmit, and here you get 4 channels. And so if I want to do something shaped, so I could say, let's do a trapezoidal pulse, And let's just leave everything as is and then just hit run. It takes a couple of seconds the first time round because you have to clear the memory, reset everything. But once you've done it the first time round, it goes pretty fast. So here we go. So I've acquired it. This is I and this is Q. So blue and red represent I and Q. And you can see I have a beautifully shaped waveform now, much better than the grunty ons and offs that I was using in Python. So this is a great way if you want to do a Barker code, for example, or any kind of phase dependent modulation on your pulses. That's all in this free piece of software that we've got that runs on MATLAB and connects directly to the Proteus arbitrary waveform transceiver. Okay, back to the slides. Now, we also talked about closed loop. So we get this back on the presentation here. So we can do onboard decisions in less than 500 nanoseconds. So if we can do an acquisition, we get I and Q. We do a data reduction. So we've seen that working today at length. So we do digital down conversion. What I haven't shown today is using the programmable FIR filter, finite impulse response filter. So you can set the taps in this guy and do some filtering. You can then process it. So there's a math block here. So you can subtract waveforms, you can do averaging, you can do FFTs in here. So it's a down conversion path that allows you to ultimately make some decision. And the decision is, should I play waveform A or play waveform B? If we go back to when we looked at the task table about 10 slides ago, this is where it happens. So in the decision, you say, oh, okay, in my task table, there was a decision block where I said, play task 4 instead of task 5. And then we play out. So we take the waveform memory, I and Q into the DAC, and boom, out we go. This is what it looks like in real life, an example actually. So we'll look at the task table after this slide, but requiring a signal, does it exceed a threshold? Yes, do 1. Does it not? Go to 2, select the waveform, play. And this is how we do it. So we say we're going to do digital trigger on. We're going to say, in this case, we're going to say, let's bypass the filter, DSP FIR select bypass on. Is the threshold, does the threshold exceed 1,000 DAC points? If yes, make the decision. If no, make the decision in the other direction. So either play segment 1 or play segment 2. So what's that look like in real life? You have to orchestrate that inside the instrumentation. You have a task table with 4 elements. This is a waveform scheduler, but I've just converted it into easy to understand English. We're just playing out DC. And then task 2 says, all right, play a Gaussian pulse. As soon as you play that Gaussian pulse, enable the DAC trigger. So that's the internal DAC trigger that I talked about earlier. Sorry, that's a typo. Trigger the ADC to make an acquisition. The ADC or the digitizer is sitting there. It gets it. It makes the acquisition. When this triggers it, it passes it to DSP. Does it exceed a threshold value? Return 0. If exceeded, return a 1. If exceeded. So DSP returns 0, go to task 4. DSP returning 1, go to task 3. So there's some more Python that I did earlier. So I generate in the waveform. I generate in the waveform table a Gaussian pulse, a square pulse, and some DC. So if the threshold's exceeded, it plays that out. If the threshold's not exceeded, it plays that out. And you can see the return, the loop time, the latency around the system is about 300 nanoseconds to make a decision directly in the FPGA. Channel-to-channel pulse alignment, spent a lot of time and energy on this. This one is, we've got the scope set to about 50 picoseconds per division. And this is channel 1 on one module. This is channel 12, 3 modules later. And we have a sync technology that we've developed that gives us very good time alignment between all the multiple channels. And of course, when you begin to stack those in the multiple chassis. Our chassis system, and the reason why we designed the 21100 chassis system is for this tight channel alignment. Every single channel, whether it be channel 1 or channel 150, has to be as coherent as we can make it in time. So we're going to conclude. Here's our scenario. We can generate multiple emitters. We can generate different frequencies. There's trade-offs, of course, with DACs and using different Nyquist zones, C-band, S-band, X-band, all achievable with different varying performance. If you get worried about that, I often sometimes match it up with an IQ modulator. We also make local oscillators that go with our system as well. And also, some people use the NCO, the numerically controlled oscillator, on one channel to be the local oscillator for an IQ modulator, external analog IQ modulator. Got some great bandwidth, 1 or 2 gigahertz, so we can do hop sequences and linear frequency modulation, pulse-to-pulse coherence. In the MATLAB I showed you, we can generate any type of pulse that we wish and put those in the scheduler. Mode emulation, so once we've got all the pulses, we can schedule out different modes, and then we have excellent channel pulse timing and alignment. So hopefully we can help generate the correct scenario. It's a modular system, as we talked about. So here I just looked at a single module can do a receive and 4 transmits, which matches a generic radar warning receiver and ECM system. And then this is the block diagram that we looked at. So 4 transmit channels, 2 receives, the fast memory inside. But if you don't want to use a fast memory inside, you want to do some more advanced, we try and get the smallest amount of data out of the instrumentation as possible. So trying to keep data transfer on this bus as small as possible. That's why we invented the task system for waveform scheduling, and that's why we have a lot of decimation and filtering here to be able to get things out quickly. So it's a modular system. You can build up you can build up as many channels as you like. Very tight coherence with our custom chassis system that we made. It conforms to PXIe standard as well, so you can put other people's modules in here as well. But it's really designed for tight time alignment across many channels. If you just want a bench unit, these modules also come in the PXI chassis, but they can also be mounted in our desktop chassis with the screen. And also we have what we call, our benchtop chassis with the screen. It works like a regular instrument. And then we also have the desk, which is essentially this bench instrument, but without the screen and keyboard. It's a lower cost, especially if you're just interested in using it for remote operation only. So I talked mainly about 9 gigasamples today, but we do 1.25 gigasamples, 2.5 gigasamples as well. So that's the Proteus arbitrary waveform transceiver system built on RF DACs and RF ADCs with a fast FPGA in the middle. And with that, I'd like to thank you all for attending. And as I said earlier, if there's any questions, please message me directly in LinkedIn, or if you have our email, info@taborelect.com. That's info@taborelect.com. We'll be happy to get back to you with any questions. And if you're interested in this system, we'd be happy to work with you on a configuration and help you develop some pulse sequences and get some emitters defined. With that, I would like to thank you all again and would sign out. So it's bye from me, and hope you have a good evening or a good rest of your day today. Thank you very much. Bye-bye, everybody.